between the two metal atoms. That is, in this figure you can see, in figure 6.20 you can see how this peer to bridges between the two metal atoms. So in equation 6.38, in this equation, an application where an intermediate forms and the design synthesis of a molybdenum tungsten compound, it happens. So here in this equation you can see this is the molybdenum complex that we have taken. This reacts with a phosphine of tungsten of W, and then the reaction takes place which forms this complex, that is the molybdenum tungsten complex. Here it is formed and BPH3 is released. So this is how we can also synthesize phosphines which contains two metal centers. And so this is an example of monophosphines. Now we will come to diphosphine ligands. So the chelated or bridged complexes, they are usually formed from the diphosphine ligands. So examples is, the most common example is what we call it as the DMPE, that is dimethyl phosphinoethane, and also DPPE, that is diphenyl phosphinoethane. So and we also have DMPM, that is bis dimethyl phosphonomethane. So some of the common examples here, it has been shown in figure 6.212. You can see this is the DMPE, the structure of DMPE, the structure of DPPE, and this is the chelated DPPM and the chelated and bridged DMPE. So this is when we have a diphosphine ligand. So mostly chelation, or that what we call it as the bridged complex, they are formed because they are bidentate in nature. Then the ligands that are here, they are shown in figure 6.23. They have been prepared in such a way, these types of ligands, so that they will form only chelates. That is, they will only form your complexes, bridged complexes. So chiral complexes, they can also serve as catalyst, and then it is required to provide chirality on complexes on or products formed. For such purpose, chiral diphosphinoethanes, they are utilized. The one that is shown in figure 6.24. So here in figure 6.24, this is a chiral diphosphinoethane. The here it is, we can see it has a chiral center that is marked by the C star in these two examples. So we see that the products given by DMPM versus DPPM or DMPP, they are all not the same, because of the arrangement of the different atoms around the phosphine molecules, diphosphine ligands. So the product that is formed when we use different types of diphosphine ligands, then the products or the complexes that are formed, they are also different. So diphosphines with long chains between the p atoms, they may occupy transposition in square complexes, or they give large ring systems, that is shown here in figure 6.25. This is a large ring diphosphine that we can show here, that here it is shown in this figure. The trans isomer, it is more soluble than the cis, where the octahedral complexes are very rare. So where such cases with the, actually this is not easily understood why the trans isomer is more stable and then the cis when the octahedral complexes are present. This is not very easily understood, but this is what it has been found. So in figure 6.26 you can see this is a cyclic diphosphine. So here two phosphine groups are there, but it is cyclic in nature. So more biphosphines which are also important in the asymmetric binapthyls, they are here in figure A. This is an asymmetric binapthyl. This is also an example of a biphosphine ligand. And the second is 1,1 dash diphosphinoperoxine. This is also an example of a diphosphine ligand. So most of these cases, when such ligands are used, the complexes that result from are usually, they are bridges or they are chelates in nature. Then after biphosphine ligands, the other is the polydentate phosphines. So polydentate phosphine means they have the ability to coordinate to more than two centers. So the tripods such as this one CH2 PR2 whole 3, this is the most important type of polydentate phosphine. So polydentate phosphine, here we can see this is an example of a most commonly employed. So also ligands such as NCH2CH2 PPH2 whole 3 or PCH2CH2 PME2 whole 3, they are also utilized in this category of polydentate phosphines. So here as we can show in equation 6.32 that the addition of another metal atom, it may take place to form a binuclear macro cycle, the one that we have shown here in how a molybdenum versus tungsten, both binuclear, the complex has been formed. Similarly in this case also it is possible for polydentate ligands, like the hydroformylation reactions here they have been shown in equation 33 and 34. In these two hydroformylation reactions, they are the largest scale of the industrial process for the generation of homogeneous catalysis. So polyphosphine complexes, mostly they are used of rhodium, they have been used. So the catalyst, they not only increase the conversion but also they do not favor the formation of undesirable products. So here an example of a racemic tetraphosphine has been shown here in 6.28. You can see it is a tetraphosphine and it serves better than the most catalysts that we use today. It serves better than them. Then this ligand, that is that is rhodium Nb2 whole 2 BF4, it forms a complex that is shown here in figure 6.29a. This is also an example of a polydentate phosphine. This undergoes reactions with COH2 mixture to form the actual catalyst. This is the actual catalyst, but it undergoes a reaction with water gas, that is CO plus H2, to form the polydentate phosphine. So after polydentate phosphine, there is another class of phosphines which are called as macrocyclic phosphine. So here only with phosphorus donors a number of macrocycles. So macrocycles means they are large molecules. That is what from polymers and macromolecules, the word they are synergistic to each other. So we can say macromolecules or macrocycles. They are the cycles having large number of molecules in them. So here the only with phosphorus donors, a number of macrocycles are there along with mixed sets of P and N or P or S donors. Like for example, macrocyclic phosphines. Here we can see for figure A, it is a PPH. The macrocycle is formed, but here in figure B, we can see the P and S donors. They have formed the phosphines. Then coming to the phosphite ligand. So when instead of R groups, OR groups are present, then it results in formation of ligands which are similar to phosphine ligands like POMe3 or RO2POPOR2. So these complexes, they are mostly similar to that of phosphines, but they have differences. What are the differences? That the phosphites are generally more basic and they are less sterically hindered, that is they have less steric hindrance. Like when we talk of a phosphine, we know that the phosphine ligand is PPH3, so here three phenyl groups are present. But when we talk of a phosphite ligand, so this phosphite ligand, it may be POPH3 or POMe3. So in such cases there is one less number of either the phenyl group or the methyl group. So methyl is okay, but since phenyl is a bulky group, so in comparison to PPH3, the phosphide group, that ligand, that is POPH3, it is less, the steric hindrance is less in case of phosphide ligand, and that is why they are sometimes more basic than the phosphines. So whenever a substitution labile ligand is present in the metal, a coordinated phosphonate results from the reaction with an alkyl phosphate. So the reaction can, some of the reactions can be shown here as, if we take POMe3 with LMNX, so here we get the coordinated complex that has been shown here in, like for here in example ruthenium complex, a ruthenium phosphide complex. When you heat it at 150 degree, then we get a coordinated phosphonate. So this in equation 6.44, with the product is called as a coordinated phosphonate. Then coming to heterocyclic phosphorus ligands. So phosphobenzenes, we know they are very popular ligands. The phosphols, that is figure here, these type of structures, they are called as phosphols. They also behave as monohaptic donors, or their pi electron density may be involved, so that they serve as bridging ligands. So these phosphols, they can be also involved in bridging ligands, like here it is shown in 6.31b. And any p or n ligand that is analogous to 2,2 bipyridine is also shown here in figure 6.31c. So phosphazines, they also behave as ligands too. So here in this figure, heterocyclic phosphorus ligands, here the phosphols, it has been shown in the figure A, it has been shown as monodentate ligands. Second, it is a phosphols which contain the pi electrons, and it enables the metal metal bonding. Here it has been bridging ligands. Since they involve metal metal bonding, so they might also be involved in bridging ligands. And in the third type, the PN ligand, which is the analogous to 2,2 bipyridine. So this is how phosphagenes, they behave as ligand in three different ways. Then coming to cyclometallic phosphine complexes. So phosphine ligands, they often engage in proton transfer reactions. So when we come across this, the proton transfer reactions, why they are involved in proton transfer reactions? It is because they are involved in proton transfer reactions to form the metal carbon bonds. One example here, it has been shown here. So here this is the phosphine ligand, and it is the reactions of PME3. Here in a simple reaction, it loses one H transfer. Owing to one H transfer, then it is shown here the metal carbon bond, here it has been formed. So here this is the product. So also we see a 4 or 5 membered heterocyclic ring also forms. So hydrogen transfer from the phenyl rings have also been observed to give the products with the unit. Sometimes such type of phosphines also undergo hydrogen transfer, and then they give the products here as it has been shown here. So two types of possibilities are here there for the hydrogen transfer in cyclated in phosphine ligands. Then coming to dialkyl diaryl phosphidoligands. So here some of the equations for the various important preparations of terming on bridging complexes, it has been shown. So as here you can see in equation 6.46. So here the LiPPH2, it forms the zirconium complex in this way. So here this method of the cleavage of the R2ppr2, or the mostly the ppc bonds, it has been known and it has been used to prepare various types of R2 antibody and R2 bismuth compounds. So we'll find various compounds which are similar to dialkyl amido compounds. These are dialkyl amino compounds of molybdenum and zirconium. However, homoleptic complexes, we know they are very rare, and usually they form bridges. Here that is shown in such type of reactions. Since this is present, so they formed a bridge complexes. Then phosphine phosphidoligands, they can be made from R2P, CH2N, PRH, and they can give complexes. This is the phosphine phosphidoligands, and such type of complex can result from the phosphine phosphidoligands. Then phosphinidine ligands, compounds with M double bond PR, they are generally intermediates that we come across, but compounds like CP2, MOP, C6H2 tertiary butyl 246, they can be isolated where R is bulky alkyl group. So what happens here is, if you see, this is the phosphinidine ligands. So this is a example of a phosphinidine ligand that has been given of the mu2 type, that is bridging ligand, and it has been shown here. So some of the examples of mu3 and mu4 complexes, it has been shown here in figure 6.35. You just have to remember the type of phosphine ligands and the different examples of the complexes that are formed by such type of phosphine ligands. Now coming to ligands with P double bond P, P double bond C and P triple bond C bonds. So this is a very peculiar case. So there are numerous phosphorus compounds that contain multiple bonds and they can form a variety of complexes. So here phosphorus and arsenic, some examples it has been shown that form multiple bonds. So like here you can see this is a P double bond P bond that is here. Here is also a P double bond P bond, and we can see here in this cases the P2 metal bond here it is coordinated to metal in different ways. So all the lone pairs they can singly or together donate, and even the multiple bond it can donate. So some real examples here it has been shown in figure this 6.37, that is compounds with multiple bonds. So this compound here, this is one example. Here it is a nickel complex example, and this one iron, and this is for tungsten. So some compounds with multiple bonds have been shown here. Then phosphoalkenes, that is Pr double bond Cr2. So they either they act as monohepto or bihepto as it has been shown here. So here in this case they act as the monohepto, but here in this case they act as the dihepto cases, the phosphoalkenes ligand. So while also phosphoalkyne ligands they have been known, but they always form dihepto complexes as here it has been shown. So with this we finish the topic on the different types of phosphines and their phosphine ligands and their examples. So this is the self assessment and the question part. You can go through, the answers has been provided, you can solve them for yourselves. So now we'll start the next part of this, the second part of this chapter. That is, in the first part, we talked about metal pi complexes, the first part. And here in this second part, that is the metal pi complexes, second part, we will talk about the alkene alkyne complexes, the cyclopentadienyl metal complexes, and other alicyclic complexes. So first we'll start with metal pi complexes with alkene, alkyne, allyldine, and cyclopentadienyl ligands. So most of the pi or donor complexes they comprise of an important class of organic compounds. So to understand this, so metal pi complexes we know they are actually very important in various parts of chemistry, like mostly in organic chemistry they are used for the preparation of various types of catalysts. They are also used in other applications such as hydrogenation, polymerization, cyclic processes. So that is why metal pi complexes they are a very important class of organic chemistry. So the types of compounds that is observed here in such classes, it has been classified, and the first class is the alkenes. It may donate an even number of electrons to a metal or metals, as here it has been shown in figure 7.1a. So ABC, you can see the ligands with alkene group. Here you can see this is the alkene group is present here. Also in figure 2 we can look into the alkene group, and the third here in figure 7.1c, this is also a ligand which contains an alkene group. So the alkene group it may donate an even number of electrons to the metals or the metals. So and these are the three possibilities of the formation of the ligands. In allyl group it may be divided, may be pi bonded also, where the allyl anion it donates 4 electrons. Like here in figure 7.2 you can see this is an allyl anion, and an allyl anion it donates 4 electrons. So then comes the alkynes. See, the alkynes it may donate one pair of pi electrons or both pairs. So these are the ligands with the alkyne group. As you can see here, they may donate one pair of pi electrons or both pair of pi electrons, and that depends upon the complexes that we are that we are working with. The fourth is the cyclopentadienyl group, that is the C5H5 ligand, and it is always eta 5, that means it is pentahepto. So it is the cyclopentadienyl, it is an anion and it donates 6 pi electrons. Here is an example of a cobalt complex which contains the pentahepto CP, that is the cyclopentadienyl group. Then the fifth class is benzene and its derivatives. We know benzene donates 6 pi electrons to a metal in the form of eta 6, that is it is hexahepto. So here in the case of chromium an example has been shown. This is a derivative of benzene. Then the last case is eta 7, that is hepta. This eta 7, it means it can donate 7 electrons. The hapticity is 7. This is cycloheptatriene and they are quite well known as the eta 7 C7H plus. It is called as tropylium ion. Now as we call this C5H5 ligand as the cyclopentadienyl, similarly this cycloheptatrienyl it is called as tropylium ion and it is represented as C7H7 plus ion. This is a remarkable feature of organic chemistry. The most common synthetic method to prepare this is to take a cycloheptatriene complex. Once we take this cycloheptatriene complex and then we react it with either PH3C plus or ET3O plus, and then as a result one proton is abstracted. So here and it have one H minus is abstracted. So here it has been shown here. So this on the left hand side, this is the cycloheptatriene complex. This is reacted with PH3C plus BO4 minus and ultimately which forms the tropylium ion, that is the C7H7 plus ion. So this is how the tropylium ion it is formed. Then coming to alkene complexes. So we find that transition metals with low valency, they form metal complexes with pi donor ligands, especially with the group 16 and group 18. So this the model which explains this is called as the DCD model or the Dewar-Chad-Duncanson model. So here this DCD model it has been shown in figure 7.6. It explains that how this sort of complexes they are formed. So here we can see that the electron C double bond pi bond it is donated to the metal in its empty orbital and thus it forms a sigma bond. So again the electron density of the filled orbital it is back donated to empty orbital, that is the pi star of the ligand system, to form the pi bond. So now this process is similar to that of the metal carbonyls that we have studied. So we see that such bonding only takes place with a low valent metal, that is when the metal lies in the mostly with the group 16 and group 18 metals where the symmetry orbitals are filled, that is a metal in the late transition series. So eta 2 alkenes are two electron neutral ligands. Here it has been shown in figure 7.6. The interaction of ethene with a metal atom, that is first the donation of electron density from the filled pi orbital. This is the here first is the formation of the sigma orbital and in the second case it is the acceptance of the electron density from a filled d pi orbital into the vacant pi star orbital of the ethene. So if we see the ethene complexes of the d metals, then we see that there is a balance between the electron donor capacity and electron acceptor capacity. But we can change the extent of donation and back donation by changing the substituents on the metal atom on the alkene. So we see that the CC bond will decrease if the pi back bonding it increases. Now why this happens? This happens because the C double bond C and anti-bonding orbital they gets the electrons and the structure becomes that of a structure with C single bond C. So here we have a metal that is coordinated with a double bond. But if the pi back bonding increases, then the C double bond C it decreases and as a result the structure becomes similar to that of a CC single bond, and this As a result of this, we call this structure as a metallocyclopropane. This is the metal that is present here, and since this is cyclic, this is called as metallocyclopropane. This nature of reversal of olefin reactivity, it is called as umpolong character. So, in the case of diheptoalkenes, the substituents they bend a little away from the metal atom, even if there is a small degree of electron donation from the metal. Also, the CC has a slightly greater bond length than that of the free alkene. So, this changes when the degree of back donation it becomes more, and the substituents on the alkene they move away from the bond metal atom. So in case so the C double bond C bond length it becomes to that of equal of a CC single length. Then coming to preparation of alkene complexes. So here the first method of preparation of alkene complexes is by direct reaction. So these are cases when coordinatively unsaturated metal complexes they react directly with the alkenes. One of the common examples is the formation of Vaska complex. The Vaska compound it forms complexes with ethylene, tetrafluoroethylene or tetracyanoethylene. Here it has been shown in equation 7.2. Here this is iridium, chlorine, CO, PPH3 whole 2. It will directly react with this is the Vaska's complex, and it will directly react with an alkene that is R2CCr2 to form this and Vaska's complex with the respective alkene. So the metal atoms, they also react directly with the alkenes and particularly the dienes producing metal pi donor complexes. For example, the tris 1,3-butadiene, molybdenum and tungsten, where the CC double bond are situated in a trigonal prismatic arrangement in such a way that the metal atom is equidistant from all the 12 carbons that is shown here. So here this is a tris 1 3-butadiene molybdenum complex. So here the position of the molybdenum, it has been molybdenum and tungsten, it has been such a way that the CC double bonds they are situated in the you can see here this is the CC double bond they are situated in the trigonal prismatic arrangement. So as a result of this the metal is that the molybdenum that is here it is equidistant from all the 12 carbons that is present. So this is how the particular these are especially the case of the dienes. Then the second method of preparation of alkene complexes is the displacement of a weakly bound ligand. So the ligands, the displaced ligands may include CO, non-conjugated or non-chelating olefins. So here in equation 7.5, an effective method for preparing palladium or platinum olefin complexes has been shown. So in this equation, we can see FeCO5 plus we see the ligand which and then with the particular displacement of the CO1 CO ligand, we see the complex has been formed. Similarly, in equation 7.5, this is a palladium complex, alkene palladium complex, and it reacts to form the typically it displaces C double bond N and then this complex palladium complex is formed. And the third method of preparation of alkene complexes is the reductive addition. So reductive addition it is a popularly it is used for platinum group metals. So here the higher valent salt of the metal it gives the alkene complex of the zero valent metal here as it is shown in equation 7.6 like PPH3 whole 2 PTCl2 plus NH2H4 ethanol plus C2H4. It gives us this complex. So this is called as reductive addition. Then coming to alkyne complexes. So broadly, alkyne complexes, they may be prepared similar to that for alkene complexes. But alkynes, they are more electronegative and they bind more strongly because of the possibility of the back donation in a better way. Also, regarding the synthesis of alkenes, follow some of the common methods are first is we know that monoalkynes they can function as 4 electron donors by utilizing both pi bonds, that is shown in equation 7.7. So here, this for this complex directly it uses, and they, because alkenes, monoalkenes, they are 4 electron donors and they can utilize the pi bonds. So unless the alkyne has bulky substituents or the complexes with divalent platinum group metals, they are unstable, so giving rise to a variety of other products like here. So some in 7.81 and 2, so different types of products are found if various if the bulky substituents are present, then the metal it decomposes, then the complex it is unstable and it leads to formation of other products. So in many other cases, alkyne polymerization it has been observed. So of this polymerization, 8 compounds have been isolated. So here FeCO5 plus PHC-CPH, it gives rise to diphenyl and various types of complexes, alkyne complexes, that has been shown here. Then coming to allyl complexes. So the allyl ligand that we know, CH2, CH, CH2 minus, it binds to a metal atom in two configurations. The first is a 2 electron donor with a single negative charge. This is the eta 1 ligand. Here it has been shown here, the, and that behaves like an almost an alkyl group. Sometimes the allyl ligand it also behave as a, mostly in all the cases it behaves as a monohapto, but in other cases it has been shown that it behaves as a trihapto. Here it has been shown how it behaves as a trihapto, and in figure 7 point here another example has been shown. Here one is the symmetrical structure and one is the curved structure. So in order to understand the bonding of an allyl group, we have to consider the molecular orbital theory. So the eta 3 bonding mode, it explains the symmetrical arrangement of the allyl ligand perfectly. So here this is the molecular orbital of the particularly the pi system of the allyl group. So here also it is shown the metal d orbitals have been shown, and their interaction it has been shown how they give rise to the eta 3 hapticity, that is trihapticity. The eta 3 allyl group, it can have the terminal substituents bent a little out of the plane of the 3 carbon backbone, which results in syn or in the anti-configuration of the respect to the central hydrogen atom. So here the equation 7.14, it shows the mechanism of the transfer of the syn form with that of the anti form. Then after the allyl complexes, we'll talk about cyclopentadienyl complexes. So here we will discuss the complexes with the cyclic pi donor pentaheptocyclopentadienyl molecule. So some of these are basically complexes that is mostly we know formed by the CP molecules, that is the cyclopentadienyl, and it is represented as C5H5 minus. So for the compound CP2 titanium, it is dark green and it also exists in the form of like this. So some of the known compounds metallocene here that has been shown here. So cyclopentadiene, that is cyclopentadiene is C5H6. It forms the cyclopentadienyl anion, that is C5H5 minus, by deprotonation. So it is a mildly acidic hydrocarbon. The aromaticity in it arises out of the 6 electrons that is present in its pi system. So the delocalization of the 6 electrons, it forms a ring, that forms of the ring uses 5 bonds that are of equal length. So that is how the C5H5 minus, that is the cyclopentadienyl ligand, has been formed. So organometallic chemistry, it is abundant with this cyclopentadienyl ligand. This CP, it may be monohapto, trihapto, or pentahapto. Also, there are complexes of monohapto cyclopentadienyl ligands. So here it has been shown how we'll also, this is an the molecular orbitals of the pi system. Here it has been shown for the cyclopentadienyl group. Then coming to the synthesis and properties. So metallocenes are actually, they are symmetrical metal compounds. First, the parent molecule, that is the C5H6, it is prepared by thermally cracking or thermal breakdown of dicyclopentadiene. So first we take the dicyclopentadiene, it is heated, it forms the cyclopentadiene. So after the cyclopentadiene has been formed, then one H plus is removed from the diene. The synthesis of here, it has been shown how do we remove this. It is done by using sodium in THF or Tl2SO4 in potassium hydroxide, and we get the cyclopentadienyl ligand. So here this is how CP5H5 minus is formed. So these CP5H5 minus or the cyclopentadienyl ions, they are not stable in water. They can be used for the direct reaction with an anhydrous salt of the metal to form the respective metallocene. Alternatively, what we can do is a hydrated metal salt, it can be used if the cyclopentadiene ion is generated in situ. So here we see a sodium C5H5 plus COCl2. So of direct of this reaction, we see the NaCl and the cobalt CP salt, the so cobalt CP complex. So in equation 7.14, here it is shown the preparation for iron CP5 HC5H52. So this is how we can also use directly the metal salt solution and react to form the respective cyclopentadienyl or the metallocene. So also a number of mixed sandwich complexes. Here you can see this is an example of a unusual metallocene with iron. So this is the example of a sandwich compound. There are also examples of mixed sandwich compounds. Here we can see in figure 7.16. So these are mixed sandwich compounds. So here it is a CP. If you take the example of cyclopentadienyl, for this particularly for the manganese. So for manganese, in this case, in the case of B, here it is cyclopentadienyl, but in the lower case it is eta 6 benzene. So this is how two different rings are present. Then that is why they are called as mixed sandwich compounds. So here the so the eta-4 cyclobutadiene complex, that is here it is shown in equation 7.7, it is prepared in a photolytic reaction that is analogous to tetrasubstituted cyclobutadiene complex. So this is how different types of this complexes or the mixed sandwich complexes, they can be prepared. So now then coming to preparation of molybdenosine. So molybdenosine, it requires the preparation, it is done in two important steps. So in the first step, what we do is here MoCl5 sodium Cp plus NaBH4. This forms the molybdenum complexes. Also, then finally it has to be purified and crystallized in NaHg, that is sodium mercury amalgam in THF, and it forms the complex. So then coming to certain reactions of molybdenosine. So here molybdenosine in general, the different intermediates have been reported, and here in some of the reactions of the molybdenosine has been shown here. Then coming to the structure and bonding of the metallocene. So ferrocene, we talked about ferrocene. The geometry of cyclopentadienyl rings, they are different in the solid state. Here ferrocene is staggered. If you look into ferrocene, that is iron is present, then it has a staggered geometry, that is D5D symmetry. But if we take ruthenocene, then here they are, it is eclipsed and it has a D5H symmetry. So that is why the cyclopentadienyl rings, it is highly dependent on the metal that is attached to itself. So it is evident here that ferrocene and its derivative in solution, they have free rotation of rings. So if you look into ferrocene, the rotation of the CP rings here, it is free. But in the here in solid state, the crystal packing force, it comes into play. In the gas phase, the barrier to rotation of the ferrocene rings, here it is just 1 kilocalorie. So Woodward in his experiment, he showed that ferrocene undergoes the Friedel-Crafts catalyzed reaction only on one ring and very less on the both the rings. So if we assume that both the two rings are free to rotate, then only one dice substituted compound can be isolated. But if there is no rotation, then the possibility of three one dice substituted isomers has been shown. So thus, but only one compound has been isolated, which supports that rotation occurs around it. So the bonding in metallocins can has also been understood from their electrochemical properties. By looking at the electrochemical properties, we can also, this there is a parameter that we call it as the Hammett and Taft function, which gives us an idea about the bonding in ferrocins. So the qualitative molecular orbital diagram for ferrocene, here it has been in this it has been shown in figure 7.21. So it is found that the metal DZX and the DYZ orbitals, they interact more strongly with the cyclopentadenyl atomic orbitals than the metal orbitals. So the molecular orbital diagram for the ferrocene and its metals, it has highly been, they are complex, and thus mostly these are studied from the NMR spectrum. So this, the contour diagram has been shown for the metal bonding in the ferrocene. So here we can see some other ferrocins. It has been shown here for titanocene, the different types of titanocene. It has been shown here. Then coming to borazine. So borazine are a particular class of organic compounds which are formed by the reaction of ammonia with diborane at 470 degrees centigrade, and it forms a compound of the chemical formula B3N3H6, which is known as borazine. That is, when diborane B2H6 is subjected to ammonia, we get borazine. So this borazine is analogous to benzene, and that is why it is sometimes called as inorganic benzene. So this is the inorganic benzene is borazine. So in table 7.2, a comparison of the physical properties of borazine and benzene, it has been shown here. So borazine, however, it is more reactive than benzene. It readily reacts with water, ethanol, and acids to yield adducts because its reaction is very fast. Borazine has a regular plain hexagonal ring structure. The B and bond distance in borazine molecule is less than the sum of the single bond covalent radii of the B and N. This indicates the presence of the pi bonding involving the lone pair of electrons on nitrogen and an empty p orbital on boron. So that is why the terminology has been shown here as borazine. So the molecular orbital calculations for this borazine, they are beyond the scope of this discussion. So the experiments between have been carried out for the reaction of water and HCl with borazine. The mechanism suggested that the boron attack, the boron undergoes a nucleophilic attack. So the results, this may be, there are other factors which also influence the reaction between borazine with HCl or with water. So then coming to arenes and other alicyclic ligands. So if we prepare dibenzene chromium and similar structures, then a different path has to be followed. Complex such as these, they are formed between a neutral ligand and a metal in a zero oxidation state. So this was first developed by Fischer, and here the co-condensation of the metal atom vapor with benzene or benzene derivatives has now been used for the synthesis of bis arenes. But arenes having halogen or basic substituents, they cannot be used for this Fischer aluminum reduction reaction. Then table 7.3, the properties of some bis arene metal complexes, it has been shown. C6H62 for vanadium, the color is black, and it is undergoes rapid oxidation in air, and some of the other properties for the metal complexes has been shown here. But there is no such disadvantage in the preparation by the vapor phase method. So therefore, what happens is chromium, molybdenum, and tungsten have been synthesized by taking this in the by condensing at minus 196 degrees centigrade. Preparation of arene metal carbonins, especially of those of group 16, it is done with the help of appropriate metal carbonyl. So here metal carbonyl For MOCS6, it has been done here, and then the particular complex or the ligand, it has been formed. So cyclobutadiene, it was first prepared in the form of its iron carbonyl complex. So this Fe2CO9, it was used to prepare the cyclobutadiene. So the also the reactive this cyclobutadiene, it is a uh, highly it is used in organic chemistry. Dibenzene chromium, here it is shown in figure 7.30. It is also an example of a symmetrical metal sandwich. It was suggested that it will exist as a both triene complexes. So here this is the dibenzene chromium, that is a triene complex, and here it is a benzene complex. So recent studies, it suggests that dibenzene chromium is a benzene complex. The bonding model for dibenzene chromium, it is almost similar to that of the ferrocene. The pi molecular orbitals of benzene, it has been shown in figure 7.31, and here it has been shown how they are similar to each other. So with this part is over, and here are some of the questions regarding this unit. So now we will start with the next unit, that is metal clusters. Now we'll just take a break of 5 minutes and again start with the metal clusters. So we'll start with the next unit, that is about metal clusters. So here metal clusters will be dealing with higher boranes. So this is mostly metal clusters. They indicate the boron based cluster chemistry. So here the metal clusters, they have been classified into two major categories. So one is the class 1 type, which the class 1 metal clusters, which is the polynuclear carbonyl, the nitrosyl and related clusters, the metals in lower oxidation state such as +1 and -1, they belong to the right hand side of the periodic table. They are in this category. The class 2 type of metal cluster, it consists of the halides and oxides of transition metal complexes in their higher oxidation states. So we know that the transition metals, they are found on the left hand side of the periodic table, that is mostly in the second row and third row. They form such type of clusters like the ReCl28, that is where the rhenium, it contains +3 oxidation state. So here we'll gradually study about class 1 and class 2 type. Then the first question that arises is, why do metal they form clusters? So because the transition metals, they have large energies of atomization, they show higher tendency to form clusters. Also, the nature of the d orbital, here it is very important. As the effective nuclear charge it increases, we know that the size of the d orbital it decreases. So when the nuclear charge is high, then the effective overlap of the d orbital it decreases, which favor the cluster formation. That is, the first row transition metal which have higher oxidation state of +2 and +3, they do not favor orbital overlap, and that is why they do not form clusters. Then the binary boron hydrogen compounds, or we call them as the boron, they are very important because they all form clusters. Why do such the boron hydrides they form clusters? It is because the borans, they are uh, have been extensively studied to for they introduce the concept of metalloborans and carborans, which have been both included in organic and inorganic chemistry. The covalent bond here, it is seen in the new light that we have not previously studied. The molecular structure of some binary hydrides, here it has been shown in figure 8.1. So here this is B4H10, B5 H9, B5H11 and other some borans. So it is known that the lower borans, that is B2H6, B4H10, they and B10H14, these are all are volatile liquids or gases. Now they have to be stored in an air-free apparatus. There are 35 neutral binary borans. Numerous organics or halo-substituted derivatives, they have been synthesized from such borans. Also, taking the boron framework, metal or non-metal heteroatoms have also been constructed. So there are polyhedral boron anions also. So if we look into this table 8.1, the neutral boron hydrides, it has been shown. So first is the B2H6, B4H10, B5H9, then like B8H18, and the list continues. We can see this is a huge list of the borans which forms the different types of borans, and their geometry has also been listed here. So these borans, so they are, since they are very widely used, they are mostly the widely sourced method of preparation of most boron was first by the pyrolysis of B2H6. Now what is this pyrolysis? Pyrolysis means controlled heating of a material in absence of air. So when diboron, that is B2H6, is subjected to pyrolysis, then the higher borans, that is the molecules which are larger than diboron, they are formed. So in organic synthesis, metal plating and bleaching of wood pulp, they find use as the reducing agents. The metal hydrides, they react with diboron or boron trihalides to form these type of compounds. So first B2H6 plus LiH, it forms LiBH4, that is lithium boron hydride. Then BCl3 plus NaH, sodium hydride, it forms NaBH4 plus NaCl. We can also obtain diborans with the help of the reactions like NaBH4 plus BF3, it forms B2H6, LaH, that is lithium aluminium hydride, plus BCl3, it forms B2H6. So in the laboratory, the best method for the preparation of diboron is the hydride abstraction of BH4 minus. BH4 minus plus BX3 in presence of DCM dichloromethane, it forms B2H6. That is, this is the most commonly used laboratory method of preparation of diboron. Now, with the help of this hydride abstraction, higher boranes they may be obtained in the volatile form of larger anions. So, thus, treatment of B3H8 minus salts with boron trihalides it gives the best available synthesis of tetraboron. Suppose we start with B3H8 and we take a boron halide. So it gives us a higher boron, that is B4H10, that is the tetraboron. Similarly, we can also obtain B5 from the lower B4 ion. So that is the pentaboron. It can be synthesized from the lower boron. So hexaboron, it also can be synthesized via insertion or addition of a boron into the bromopentane framework. Here it has been shown in equation 8.9. So we have one, this is the B5H8 bromide, which after we will insert reacting with B2H6, it introduces a boron to the B5, the pentaboron framework or the backbone, and then the higher hexaboron here it is formed. Then is the decarboron. It is the smallest solid boron. It can be prepared from BH4 minus by the process. Here the equations it has been shown in B from 2 pentaboron it forms B10H14, and also this pentaboron it forms B10H14, that is by the hydride abstraction and also by the metal promoted fusion reactions. So of the characterized higher borans larger than B10H14, all boranes except the B11H15 they consist of two or more cluster units that are joined in some manner. Like examples of synthesis, here it has been shown in 8.12 to 15. This is B5H9 plus H2, that in presence of an electric discharge it forms B5H8. So the formation here for B12H16, it is the only neutral dodecaboron. It is formed by the metal promoted fusion, that is B6H9. It is passed through or it is finely divided iron, then we get the dodecaboron. So then coming to polyhedral preparation of polyhedral boron anions. So the boron anions, that is BnH2 and 2 minus, they are found for n is equal to 6 to 12. So they are deltahedral clusters. So deltahedral cluster means the polyhedrons which have only triangular faces. That is here it is shown in figure 8.2. These are deltahedral structures. So compared to neutral boranes, these anions they are more stable, especially the B10H10 2 minus and B12H12 2 minus. So another striking difference from the neutral hydrides is that the BnHN2 minus dianions they are highly soluble in water and form stable aqueous solutions. So mostly these anions are formed by condensing small boron fragments. So here 2NaBH4 plus diboron in triethylamine it forms Na2B12H12, it forms the higher dodecaboron salts. So B10H12 2 minus it is easily synthesized by the reaction of B10H14 with triethylamine in boiling xylene. So this is it has been formed. Then coming to structures and bonding in borane. So we know borane they have been classified into three types: nido, arachno, and closo. So the closo it indicates a closed polyhedral geometry which is of the type BnH2n 2 minus. But the neutral boranes they have open structure. So if we remove one vertex from a closo structure, we get a nido structure. Again, the removal of two or three vertex, it gives us a arachno. If we remove two vertex, it gives us a arachno. And if we remove three vertex, it gives us a hypno. So here it has been shown here in figure 8.3. So here this is a six vertex closed framework, that is closo. If we remove one vertex, then it becomes, you can see one vertex has been removed, it is a nido. And here two vertices they have been removed, like one has been removed from here and one has been removed from here, they are called as arachno. And if we remove three vertices, then the framework it is called as the hypo. So this principle, the boron frameworks, here it has been shown for B6, H6, 2 minus, nido and arachno. So here if we look into the 8 figure 8.4, the structure of B2H6, here it has been shown. This is diborane, that is B2H6. It has a very unique structure. So here we know that this is the actual structure of the B2H6. Here in this structure, the four terminal BH bonds and two 3 center BHB bonds are present. So this are the four terminal. This is a BH bond 1. This is the 2. This BH bond is the third terminal, and this is the fourth terminal BH bonds. And also there is two bridging BHB bonds. So this is one bridging BHB bond, and this the other is the lower one, that is the second BHB bond. So here each boron atom, it has four valence electrons, that is mostly sp3 orbitals, and that can accommodate 12 valence electrons. So this structure of diborane, it is analogous to ethylene. It is also that B2H6 is isoelectronic to ethylene, and these bridges, they are regarded as protonated double bond. So in B2H6 and C2H4, there is no deficiency of electrons because all the bonding orbitals, they are filled. However, the fragments, that is BH3, they are electron deficient. Now, if we apply the valence bond approach to neutral boranes, then the localized 2 center and the 3 center bonds, they may be utilized. So we'll apply this valence bond to B6H10, that is here it is shown in figure 8.5. So in figure 8.5a, the pentagonal pyramidal geometrical structure is shown, and in figure 8.5b, the 6 center bonds plus the 2 center bonds, here it has been shown. So if we apply that, and then here we can find out the valence bond approach. Then coming to Wade's rule. So here this is also called as polyhedral skeletal electron pair theory. So this is since this was developed by the person named Wade, and it is called as the Wade's rules. So what does this rule say? The first point is polyhedral clusters, they are assemblies of building block units such as either BH, CH, COCP or FeCO3. Now, these units, they contribute to skeletal bonding a particular number of electrons. So those available after the bonding and non-bonding electrons, they have been taken care of. Then the remaining electrons that are present in the skeleton, that it takes into account. The cluster geometry, it is found out from the total number of skeletal bonding pairs from all of the individual building block units. Here it is assumed that each unit gives 3 orbitals for construction of skeletal MOs. So it results in 3 NMOs, and so it results in 3 NMOs in an n vertex position. So theoretically, it has been found that n plus 1 of these MOs will be bonding, and the n's for particular for n skeletal units. Now, taking a closer polyhedral system, if one or more vertices are removed, then there is no change in the number of the skeletal bonding MOs. Then the capping. So here there is an important point. Let us consider a 6 vertex closo cluster. So if the adjacent vertices, they are removed, then it forms a 5 vertex nido cluster. So but if the non adjacent vertices are removed, then it forms a 4 vertex arachno cluster. So all have 6 bonding ZMOs, and therefore they require 7 bonding electron pairs. So if the number of vertices is n, then n plus 1, n plus 2, n plus 3, n plus 4, they are required for closo, nido, arachno and hypoclusters respectively. This point, it has to be remembered carefully. And the fourth point is the capping principle. It states that the capping is done on a triangular face of a closo cluster. So if we add a 7th vertex to a octahedron, then there is no change in the number of skeletal bonding. So we can say that a 7 vertex capped octahedron, it will have a 7 bonding pairs, and that is in general we can say that n vertex capped closo cluster will have n bonding pairs. So we'll take the example and understand Wade's rules. So if we take the BH bond, two of the four electrons are in it. So the skeletal contribution of BH always it becomes 2. This is we have to remember. So in this way we can see that a CH group they are 3 electron donors, but BHB bridging bonding they are extra terminal electrons and they contain 1 electron each. So let us take the example of B5H9. That is here it has been shown in figure 8.1 and 8.3 B5H9. So in B5H9 there are 5 BH units and 4 bridging hydrogen atoms. So since there are 5 BH unit, we know that 1 BH unit it will contribute 2 electrons. So 5 BH unit it will give us 10 electrons, and there are 4 bridging hydrogen electrons. So they and this bridging hydrogen electron it contributes 1 electron each. So therefore it becomes 10 plus 4 it is 14. So overall it becomes B is 7 pairs. So now here we have to find N. So N is equal to 5. That is why since the boron here it is present in 5. So N is 5 and we have 7 pairs. So this is a N plus 2 electron pair. And here we have studied that if it is a N plus 2, then it forms the nido structure. It is a square pyramid which matches its structure. So this is how we calculate the weights rule. We apply the weights rule. So next we will consider another example, that is for B10H10. This has 4 BH groups and 6 extra hydrogens. So 4 BH means the contribution is 8 and 6 hydrogen means the contribution is 6. So 8 plus 6 is equal to 14, and we say this is 7 pairs. So then here the N here is equal to, for particular system there is, this is an N plus 3 pair system, because here N is equal to 4. We see here N is equal to 4 and it forms an arachno structure. So this is how we apply Weights rules to understand the different structures of boranes. So now coming to the next part, that is the carborans, metalloborans and metallocarborans. Metalloborans, metallocarborans. So what is this carboran? So carboran they are a special class of boron cluster which contains carbon atoms in the boron framework. So they were first discovered in 1915s and they have been used for various types of applications. So some examples are FbC4H4Bf. This is a cyclic planar structure, but its hydrogen counterpart, that is H4C4B2H2, it is a pentagonal bipyramidal nidocarbon. So we'll start with closocarborins. So here we know that BnH2n they are dianines. Closocarborins they are also similar to this uh, closoborins. So here we can see the dicarbon series for the closocarborins. Here you can see for the vertices, this is the dicarbon series it has been shown, and the geometry has been predicted. So here we should note that the N vertex carborins they show similar gauge geometry by corresponding with its corresponding BnH2n 2 minus dianion. But C2B3H5 it has no known B5H5 2 minus analog. So using the Weights rules, where each CH unit it contributes 3 electrons, and we know that each BH unit it contributes 2 electrons. The total electron count here it becomes 2n plus 2n plus 1, which suggests the closo structures. So this is how we can actually predict the geometry of the carborins using from the Weights rules. So this method has also been applied. So here in figure 8.8, some of the carborins, the structure of closocarborins, it has been shown here. So these are also what we call it as the carbonage cages. These carborane cages they have applications in the field of plastics, elastomers, and other oils. Even if they are also used in tubes, gaskets, and high temperature chromatography. And then another series of closocarborins, which is isoelectronic with the BnH2n dianions and the neutral C2B compounds, are the monocarbon anions, that is CBn-1 HN minus. So various routes of preparations has been done, and one example it has been shown here for the closo, which is the C, B, N minus 1 and HN type of carborans that has been formed here. Then coming to polyhedral rearrangements. Intramolecular rearrangement of the cage skeleton, it is common for chlorocarborans and other polyhedral boron clusters. So in this way, thermal isomerization takes place. Those isomers which have maximum CC separation, they are capable of separating the relatively positive cage carbon nuclei. So following examples, octahedral 1,2 C2 before H6, it converts to the 1,6 isomers. So there is also a possibility of this intraconversion or intramolecular rearrangement. Even icosahedral C2B10H12, it undergoes intramolecular rearrangement to form the 1,7 isomer. So however, these are all possible at elevated temperatures. So the mechanism of this intramolecular rearrangement, it involves many pathways. So Lipscomb, he proposed the diamond square diamond, that is the DSD processes, that is shown here in figure 8.9. So the rotation of the faces is in the cubo-octahedral intermediate is involved in it. So this is the DSD process. Then coming to nido and arachnocarborans. So open cage geometry carborans, they are more in number and diversified. They are structurally compared to the closo series. They are listed in table 8.3 and the selected examples here it has been shown in figure 8.10. The icosahedral, the isoelectronic and isostructural analogous of B5H9, it is the nido C2B3H7. It is unstable and polymerizes in the liquid state to form a white solid. Here open cage carborans, it has been shown and the table shows all the values. So now coming to metalloborans and metallocarborans. So we could see that the synthesis of nido C2B9H12, which was done by Hawthorne. So while doing this, it was found that C2B3 open phase in this species, it was similar to the CpH5 minus ion, that is the cyclopentadienyl ion, which suggested that the transition metal ions, they can precipitate to form the coordinated sandwich complexes which are similar to the metallocene. Henceforth, it was supported by experiment that the metallocarborane chemistry was further developed. The metallocarboranes, the polyhedral metalloboranes, metal carborane complexes, they form the rich group of metal clusters. So first is the metalloborane. So metalloborane are borane cages which contain one or more metal atoms but no carbon atoms in the skeletal framework. So metalloboranes, they are borane cages which contain one or more metal atoms but no carbon atoms in the skeletal framework. So here carbon is missing. In figure here you can see 8.11 some closo metalloboranes, they have been shown here. So a number of metalloboranes are not the small, they not only contain the 4 and 5 vertices but also multi cages they are possible. These may be formed by the reaction of boron hydrides and neutral metal reagents, or more commonly between boron hydride anions and cationic metals. So most of them cannot be controlled, and that is why multi cages are also possible. So if one metal atom it gets into the cage, then additional reaction that results in the di or even trimetallic products as well as isomers are triggered. So this happens as the borane substrates, especially the smaller ones, they become more reactive towards the reagents. So this results in the formation of a mixture of various types of species of metalloboranes. So for example, both the nido complex of CpCOB4H8 and a family of CO2, CO3 and cobalt-4 closometalloboranes, they were the first closometalloborane clusters which could be obtained with the reaction of C5H5 8 with COCl2 and NaCp. So this is why we cannot control the formation of the mixture of the metalloboranes by this process. So previously we know that the Wade's rule, and we can find the structural patterns in metalloboranes from them. This Wade's rule is also applied to metal containing clusters. It is assumed that each metal atom that occupies a vertex in the cage, it uses three orbitals for bridging, and in the case of main group metals, four valence electrons orbitals they are used. So after this the calculation it has been done. So that is the electron configuration of a metal ligand unit. It has been shown pictorially. So here one orbital, that is two electrons for bonding to H, and three electrons, that is three orbitals, that is two electrons, that is bonding to Kh. So the Fe end here we can see that for particularly the FeCO3 fragment, it is found to be a 2 electron donor, while the CpNi supplies 3 electrons. So these are the some of the rules that we need to be, that needs to be taken care of while applying the Wade's rules. So the Wade's rule is also found to be obeyed by the metalloboranes in most cases. That is, the closest species, they adopt the polyhedral structures of their isoelectronic B and H2N minus, that analogs, and the open cage complexes, they having the geometries of their neutral borane counterparts. But there are also exceptions to these rules. For example, the CP4, M4, B4, H4 clusters, they have 16 and 20 skeletal electrons, but they adopt closo 8 vertex polyhedral structures, that is similar to B8H82 minus, which is an 18 electron system. So this another case is the bis dicarbonyl complex of the type MC2B9H12 whole 2. So here more than 13 bonding pairs per cage has been observed. So this slippage distortion is different from closer to nido cage, and this is an exception. So metallocarbons, they have both metal and carbon atoms in the cage skeleton. So while synthesizing the metallocarbons at lower room temperature by inserting metals into carboranes, the reaction is found to be more controlled than that in the synthesis of metalloboranes. So here this happens as the reaction happens in a particular phase rather than a single isomer is formed. So here it has been shown in the different types of reactions. So in figure 8.14, some structures of metallocarbonates, it has been shown. The PACPT rules or the Wade's rules, they are followed by them. Even though most of the metallocarbonates have two carbon atoms per cage, 1, 3 and 4 metallocarbonates are also found. Almost all of the transition metals, many lanthanoids and numerous main group metals, they form such complexes. Since it is easier to control the reaction of the metallocarbonates compared to metalloboranes, so metallocarbonates, they have been studied in details. The closometallocarbonates, they exhibit reactions that is typical of the carbonates, including the substitution of the carbon via C-lithiated derivatives, cage expansion and other processes. So that is why metallocarbonates, they have been studied in details rather to the carbonates. There is heteroboranes or the heteroboron clusters. Those are the cages which contain one or more non-metal atoms in the framework. So here that is why they are called as heterocarbonates. They include elements like from the group 13, 14, 15 and 16. Even electropositive as sodium, they can also be present. Since other than our boron, they contain a different metal, that is why they are called as a heteroborane. So here Icosahedral species such as P, C, B10, H10, P2, B10, H10, these are all isoelectronic with C10, B10, H12. Heterometalloborins and heterometallocarborins, they are obtained when transition metals they are put into the heteroborin cage framework. So here some of the synthesis it has been shown. This is called as the multi-decker metal sandwich complexes. So these complexes they utilize carborane, that is C2B3, or the organoborane, which bind metal atoms on both sides of the ring plane. Although they fulfill the definition of metallocarbonates, they are also organic complexes, organometallic complexes as well. So here in this chapter, we studied about Wade rules and the different types of boron complexes. So these are some of the questions that are associated with this chapter. Then coming to the next unit, that is the metal clusters part 2. So these are the first we will study about the compounds with metal multiple bonds. So first we have compounds with metal bonds were first known, but then there was the development of this metal bonds having with multiple bonds, they were also studied. So specifically we know that the bond between two transition metal atoms, the bond is between that, particularly a metal bond, it means that the bond is between two metal centers. This bond it may be single, double, or even quadruple. The transition metals they have n plus 1s, n plus 1p, and nd orbitals. So many clusters, metal clusters, they show three major types of bondings. One is the covalent bondings, dative bondings, and weak metal interactions. So first we will study the covalent bonding. Covalent bonding is the most common type of metal bond. These bonds they may range from single up to quadruple metal bond. So each bond between the two metal atoms, they have a single electron from each metal atom. That is examples of multiple bond atoms. Here we can show here. Here it is MO. This is multiple bond. This is chromium multiple bond. Here also in this example we see rhenium. It also has multiple bonds. So here in this table, the basis for which the cluster formation is determined, here it has been shown. The number of bonds between the two metal atoms increases with increasing the number of electrons. So when D8 or D10 electronic configuration arise, the antibonding orbital they gets filled and the chance of bond formation becomes less. So as a result, in the case of D8 or D10, there is no bond occurs and there is symmetry interaction. Suppose the electron count is D1 and D1 for both the metal, then a single bond is formed. If it is D2, then a double bond. A D3, it indicates a triple bond. A D4, it indicates a quadruple bond. D5 also indicates a triple bond. DC indicates a double bond. And D7 shows a single bond. So this is how the covalent bonding it works between the different types of metals. Then coming to dative bond. Dative bond we know it is represented by an arrow. Now this arises due to the donation of a lone pair of electron of the one metal which has filled the orbitals, and that can coordinate to another metal atom that has empty d orbital. So this say for example the bimetallic nickel complex here we have shown. So here in this case, this nickel it contains a lone pair of electrons. That is, and this nickel, the second nickel, that is, it contains an empty d orbital. That is why this nickel here on the right hand side, it can donate a lone pair of electron to the nickel on the left hand side, and it is indicated by a dative bond. Then coming to weak metal symmetry interactions. The symmetrical overlap of molecular orbital, they give rise to weak metal symmetry interactions. This overlap is generally between the filled and empty metal bonding and or the antibonding orbitals. Harry Gray was the first scientist who proposed this weak metal symmetrical interactions. For example, the iridium tetrakis isocyanide complex, it forms oligomeric chains. So here This is one chain, here it is another chain, and this is the third chain. So this is the oligomeric chain. So once when we see the oligomeric chain, so here we see that one chain is stacked upon another. So that is why this gives rise to the metal metal interaction in the form of stacks, or what we call it as the symmetry interactions. Then coming to the principal types of compounds having multiple metal-metal bonds. So here we will talk about four principal type of compounds which has multiple metal-metal bonds. It's like the first is the edge sharing by octahedra. So here in figure 9.5, you can see the 3D overlaps for edge sharing by octahedral structure. So in 9.4a and b, here we see the examples of molecules which show single and double bonds. That is, the single is the sigma square and double is the sigma square pi square bonds. So when two d4 metals interact, so both the types of orbitals they are filled. So instead of a probable triple bond, the double bond it exists. So in similar lines, for a D3 system, the bond order may be 1 and may not be 3. So this is a molecule, it shows sigma square bond, and here it is showing for sigma square pi square double bonds. Here in figure 9.5a, the possible DD overlaps in a bioctahedral edge sharing bioctahedral structure. It has been shown, and this is the orbital energy level diagram. Then coming to phase sharing bioctahedra. So the WW, that is the tungsten bond, tungsten metal bond in the W2Cl9. Here it is shown in this figure 9.6. So this is actually the first example of a metal metal triple bond. The figure 9.7, it shows the structure of the general type of compounds between the niobium and tantalum having MM double bonds. Then tetragonal prismatic structures. These group of compounds, they have MM bonds up to quadruple, and they have been studied in detail. That is ReCl28 and MO2Cl8. These are some of the most common examples having tetragonal prismatic structures. So here in figure 9.8, the five possible overlap of the d orbitals on the metal atoms, it has been shown here. So here these overlaps, the five out of these five overlaps, they are the sigma, pi and delta. The possible MM overlaps within this structure is here you can see. So this is how the different types of overlaps occur between the 5d orbitals of the metal, and we can understand how the bonds are formed. So with the help of the molecular orbital theory, the overlap of various orbitals to form three types of bond, that is the sigma, pi and delta, it has been shown. So we have to now see the d orbitals overlap on the adjacent metals so that the following cases arise. So each atom on the two metal, it gives this dz square orbital for overlap, and a sigma bond is formed. The dzx and yz, they form the two pi bonds. Then the two delta bonds, they arise from the face to face overlap of xy and x square y square orbital. This x square y square orbital is also utilized for bonding with ligand. So this is how different bonding arises. The electron configuration of metal-metal quadruple bond has been found to be sigma square, pi square, delta square from molecular orbital theory. How this occurs? Then this dxy and dxy overlap also gives rise to a strong sigma bond, and it becomes maximum when the two Ml4 halves are present in a eclipsed position. Then coming to trigonal antiprismatic structure. So here in this figure 9.10, it is an example of a trigonal antiprismatic pattern. The six ligands, they approach the metal in the manner as here it has been shown in an ethane-like pattern which favors the formation of triple bonds with sigma 2 pi 2 configuration. Molybdenum and tungsten, they generally form such type of complexes. Then coming to quadruple bonds in metal clusters. The delta orbital that is involved in the quadruple bond is weakly bonding, and the delta orbital star, it is weakly antibonding. So their separation, since they are very weakly bonding, therefore the separation or the energy gap is very small. The characteristic absorption band for quadruply bonded clusters, it results from the excitation of an electron from a singlet ground state to the singlet excited state. So these sort of transitions, they give color to the particular clusters, like Re2Cl8, it has a royal blue color. MO2Cl8, it has an intense red color. Now, because of the weakness of the sigma bond, the gain or loss of the electrons from the delta or delta star orbitals only a slight effect on the strength of the mm bond. So here it is the metal metal bond, and the here it has been shown how what is their relative strength. The formal bond order, it changes from 3 through 3.5 to 4 when the delta star electrons are removed, but there is a very small change in the rhenium rhenium distance, that is the metal metal distance. This happens as the d orbitals it contract, making poorer overlap in the pi bond, so there is a simultaneous increase in the oxidation state. So figure 9.11, it shows how one can add or delete the electrons by taking the non-bonding character. So some of the examples here it has been shown given here. Then coming to dinuclear clusters. So here this will talk about different metal atom cluster compounds and their metal carbonyl type clusters. So here in dinuclear clusters is an example, that is the Re2X8. This is a very common dinuclear cluster and it was first studied by F.A. Cotton. The rhenium-rhenium distance did not match. It was found to be 274, but it did not match with the theoretical value of 275. Then the concept of this quadruple bond between the two rhenium centers, it was then proposed by Cotton, who found the distance to be 224, and this is how the staggered conformation of it results. The rhenium Re2Cl8 is formed, which results in the formation of an anti-prism structure. The metal-metal multiple bonded clusters, they are also found in the hexalkoxodinuclear tungsten and molybdenum complexes of the formula MOOR6. Then is the trinuclear cluster. So among is the one of the most common examples is Re3Cl9, that is the rhenium trihalide. The rhenium atom, it forms the triangle here, it as it is shown here. Then above and below are the rhenium triangular planes to which the Cl minus ions they are present. Then tetranuclear cluster. So many tetranuclear carbonyl clusters they are found. So they where most of them exist as halide or oxides of tungsten. For example, W2OR6 dimerizes to form W4OR12, that is a tetranuclear cluster. So then is the hexanuclear cluster. So the first type of hexanuclear clusters out of the metal chloride is the octahedron of 6 metal that is surrounded by 8 chloride ions on the face of a octahedron. So here the first example is MO6Cl8 2 minus, and in the second case is the M6X12. So here the 12 halide ions they are surrounding the metal octahedron. So two types of possible structures are possible for hexanuclear cluster. Then coming to metal atom cluster compounds. So the study of compounds that containing metal atom clusters was very difficult to understand. So compounds like W2Cl9, MO6Cl8, they were, although they were discovered, but their structure was analyzed much later. So the discovery of Re3Cl12, it actually gained the interest in this field. Many metal cluster atom cluster, they should be restricted to cases where two or more metals they form a group in which there are direct bond between the metal atoms. The classical polynuclear complexes in which the metal atoms are held together by MXM bridge, they are not metal clusters. Like Fe4S4 aggregates in ferredoxins, where there are direct bonding or borderline cases. There are two main classes of metal atom cluster compounds which are generally found. So first is those with the metal atoms in very low formal oxidation state. That is mostly the CO. They act as ligand here. Those in which the metal atoms are in higher oxidation state. That is +2 to +4. So it is because only these two classes they have been divided into these two classes. So coming to metal carbonyl type clusters. So they are, we know metal carbonyl type clusters we have studied. It is their dinuclear, such as Mn2, CO10, CO2, Cr9. There are also trinuclear clusters are also possible. That is M3, CO12 clusters have been also studied for Fe, iron, Ru, and osmium. So here the has been shown the trinuclear cluster for osmium. It has been shown here in figure 9.16. So most reactive derivatives, they can be obtained from Ru3CO12 and osmium-3CO12 clusters. So 3 points of important points are: if we replace one or two CO ligands with CH3CN, then a more reactive species is generated. So some of the chemistry here, it has been shown that here is the cluster, and we remove it one CO, it has been removed by NCMe, then we get a more reactive species which forms other new compounds. Then in the second case, here in this given equation is the reaction of osmium 3 CO12 with hydrogen at 125 degrees centigrade and unsaturated and reactive H2OS CO10, it is formed. Here also in scheme 9.2, here in this equation, the reactions show how first OS3 CO12 with KOH, it gives the ion which is further converted to other derivatives. So this type of interaction is different, and it is called as agostic reactions. Then anionic and hydrido clusters. These are found much in large numbers. If we count the total electrons in them, we will see that one CO, it can be replaced by two hydrogen atoms, the one H and one negative charge, and two negative charges. So the protonation or deprotonation reactions, it takes place, and there is no change in the cluster structure as a result. Exceptions happen here as shown in equation 9.1. This is how an exception happens, and the anionic and the hydrido clusters, they are formed. So large clusters, they are strong polyacids in many cases. So it is difficult to isolate and characterize them, as different species may be formed together at different stages of ionization occur. Also, we have seen that neutron diffraction studies have given us the following results: that this has one RUR stage symmetrically bridged by the hydrogen, the osmium 4 H4 CO11, and POMe3, it has four bridged edges, and the hydrogen occupy the position in this octahedral cluster. So look, based from the XRD data, the structure was designated to be found to be this. So there, thus the four major types of structure can be categorized as closed polyhedra. Either it is a octahedron, trigonal pyramidal, trigonally distorted octahedron, or a cube. It may be closed pack arrays, stacked triangular arrays, and racks. The triangular faces in these, they are maybe they are exposed, that is they are open, and it may be increased by keeping one or more of these faces by another metal atom, then coming to synthesis of metal clusters. Not much mechanism has been studied for these, and generally reactive fragments, they combine to form the clusters. These fragments, they can be produced either thermally, photolytically, or by reduction processes. A very efficient mode of preparing these clusters is the pyrolysis reaction. So here this is done by using pyridine or CH3CN in milder conditions, then pyrolysis is carried out. Vacuum pyrolysis of osmium 3 CO12, it gives rise to a large number of osmium clusters. So here in presence of pyridine, we can find out here is the cluster. So in this way, other carbido clusters may be formed. Although milder pathways have also been used for such type of reactions, the milder pathways, they are found in thermal reactions where partially substituted starting materials, they provide a mean to enlarge the medium sized clusters. Large clusters, they are synthesized in a milder thermal pathway by ligands with unshared electron pairs. So here in example scheme 9.3, the reaction takes place between a cluster containing one or more labile ligands and a cluster with a capping sulfur atom whose lone pair may precipitate. So reactive anionic intermediates may be generated by reduction. Then they condense to form large clusters of the cobalt and nickel subgroups, and that is they are converted to treatment with metals in THF to form the corresponding clusters. Atoms may be introduced by addition of CCl4 C2CH6 to produce the required cluster. Heteronuclear products that has been shown here in 9.4 and equation 9.3, with the help of they may be prepared with the help of a reaction between carbonyl metalates and neutral carbonyls having a different metal. This is rhodium CO515 plus NiCO4. They form this product. Platinum, it forms this type of product. Also, simple metal halides, they may react with carbonyl anions to form metal clusters of this type. The structure of the gold nickel cluster has tetrahedral symmetry with the metal core. For example, the 18 vertex polyhedron, it is actually a face to face condensation of 4 octahedral complexes. This is an condensation of 4 AU3 Ni3 fragments to form the AUC octahedron. So the super large clusters as that of the anion, which contains 5 central layer of metal atoms stacked in the same manner as that found in a hexagonally closed packed metal, has also been found. So the presence of heteroatoms it associated with the metal atom clusters has already been studied. Apart from H and C atoms, N, P, arsenic, and sulfur, they are also fairly present. Nitrogen containing clusters have also been found of this type. Then coming to the electron counting in medium sized clusters and the capping rule. So for polyhedral clusters, because the faces are all triangular, the weights rules are used. Weight first drew attention to the similarity of MCO3 unit, that is for the BH or the CH unit. So here then the following rules were proposed. The 2n plus 2 rule for closoboranes would apply to closometal clusters. The 2n plus 4 and 2n plus 6 electron rule, it would be applied for the stable metal clusters for nido and arachno structures, and hydrogen atoms are assumed to contribute 1 electron each to the interstitial carbon substitutes. For that contributes to the 4 electrons. So while the number of the skeleton electron pairs, it is at the root of the correlation procedures, the total electron count has to be first known, and this TEC, that is the total electron count, can be calculated from the following contributions. So for osmium 6 cluster, the total number of valence shell electrons is 6 into 8. This is, we will always consider the valence shell electrons. So here 6 osmium and 8, it is 48. Now for this is 2 electrons, they contribute for the each CO group and 1 electron for each negative charge. So the total number of valence electrons for a hetero and interstitial stratum, here it has been given here. Let us take the example of osmium 5 CO16. So for osmium, the total electron count, it will be osmium, it is 8, it is present in 5, so it is 5 into 8. For carbonyl, electron contribution is 2 and it is present in 16, so it is 16 into 2. So the total electron count, it is given as 72. Then the total number of skeletal electron pairs, it will be given as 86 minus 6 into the 12, that is and the half of that, that is 7. So the vertices of the parent is 5 and the number of electron pairs is 7, so it is 5. So this is closo. So this is how we predict the correct total electron count for closo, nido, or arachno structure based on the weights rules. So while we also have to take a few rules into consideration while we predicting the total count for a closo polyhedral cluster of n vertices, the result will be 12 plus 12n plus 2n plus 1. For nido clusters, it will be from an n vertex, by the there will be 12 less fewer total electrons, and for arachno clusters that are derived from an n vertex polyhedron, there will be 24 less electrons. The predictions for TEC can therefore be stated in the following equation, that is closo 12n plus 2n minus 1, nido is 12n minus 1 plus 2n plus 1, and arachno is 12n minus 2 plus 2n plus 1. So here an example has been described for RH6CO6 how we can calculate the TEC. Then comes the capping rule. So the electron counting rules, it has been discussed. The addition of a capping rule means just by increasing the total electron count by 12 electrons. So for OS7 CO12, the total capping rule, the total electron count is 98. But then subtracting and dividing by 2, we obtain here that S is equal to 7. So the prediction of 6 vertex central polyhedron, it is closoctahedron, it is and kept on one side, it is also, it is correct. So the TC and some of the predicted structures of some carbonyl clusters, it has been listed here. Then coming to the limitation and exception, the transition metal complexes, they although we apply this rule, so they have a certain limitations. So first is the basically the rules that we have followed was that the number of atoms and number of electrons on the individual polyhedron, it should be known. Then we will talk, it is necessary note the polyhedron electron count, or with that it's called as the total electron count. And then we can apply this procedure only for metal carbonyl clusters only. So here the electron count of individual polyhedron used in the condensation process has been shown, but we cannot predict which isomer will be the help of the capping rules. So the capping rule does not define how, what type of isomer it is formed. So here an example for it has been shown that it is inefficient for identification of an isomer. So this is all about metal clusters and the keeping rule. And with this, this unit is over. These are some of the questions that you can go through. So the remaining part will be covered up in next class. So thank you for today.